Hello everyone. So from today onwards, I'll be presenting the literature around computer vision, specifically image classifications and a family of models, neural networks, which we know as convolutional neural networks, and what is the different kind of architectures that are being presented or different kind of CNN that have emerged in the ImageNet literature. So we'll shortly be touching upon what ImageNet is and later on move into a variety of CNNs. So yeah. Moving forward from here, so we will be covering what ImageNet dataset is and what was the associated challenge at first. We'll also see some of the basic computer vision tasks. Okay, starting from classification and a variety of tasks would be there. We'll also touch upon what are neural networks and basically how the basic idea of neural network is different from a CNN and which encompasses the other one. So we'll also down the line we'll be looking into different variety of CNN architectures, like starting from 2012, which marked the first SOTA, which is state of the art performance, till what was the latest architecture in 2022. And we will be covering this into a series of videos, so not entire thing would be covered into one thing. So we will dive into the ImageNet literature to understand, like from the very first model, which was AlexNet, that come out to be in 2012, to the latest model, which was in 2022, which was ConNext. And also there is an active variety of research going on into this space. We'll see what are the different kind of innovations, and moving to the latest literature down the line, we will also see that, okay, what are the current directions people are taking into. We will look into the standard training and inference procedures that are used for each paper. And there are certain procedures which are reproduced across a variety of literature. So we'll be looking for them from the reproducibility point of view. So not only we'll be covering the literature, but we'll also try to understand how and why these models work. So we'll deep dive into at some point of time that, okay, what are the essential components that are helping us work of everything. So not only the standard papers in which the architectures were presented, but we'll also be covering some set of papers, some additional papers which marks some issue around like ImageNet data and why some models are working or misbehavior of certain models. So along with the ImageNet literature, the associated literature which tries to capture the adverse behavior or even the positive behavior, and like why these models are kind of working, so they will be captured. So starting from like what is ImageNet? So ImageNet, when I say ImageNet, it is actually a data set, and but there is also a challenge associated with it. So ImageNet as a data set, it contains 14 million images containing of 21 approximately 21,000 classes. And these classes were actually organized according to the WordNet hierarchy. So WordNet is a hierarchy of nouns, and for each class we have some set of images into the ImageNet data. These images were collected and labeled by human labelers in using the Amazon's mechanical Turk-based crowdsourcing tool. So, like from the very beginning, it is crowdsourcing, and the labels will down the line, and also in different literatures. Like even from the first paper in AlexNet, we will see that, okay, there are certain labeling issues. The competition which was associated with this dataset is ILS-VRC, which is ImageNet Large Scale Visual Recognition Challenge. So this challenge actually has three tasks, but the two of interest for us are classification and the localization part. We will be looking into the next few slides what is the classification and localization kind of thing. But actually, it is the dataset for this challenge is actually built on a subset of 1,000 classes, not containing the all of 21,000 classes, and it contains 1.43 million images. So approximately 10% of the total ImageNet data was used in this. These 1.43 million images are actually divided into multiple parts, which where I can say that, okay, 1.2 million images are in training, and remaining of the images are split into validation and test set. The original dataset was released first in 2012 or 2010, but the subset was standardized from 2012 with only minor corrections. So yeah, but from 2012 onwards, like I would say that private test set was used. So the test set labels are not known to the public at large, and metrics are typically generally reported in literature onto the public validation set. So dataset currently, as of now, it is available on Kaggle, so you can download it. It is approximately 150 GB of data. And test set results can be obtained after submitting your CSV file of the in a prediction format uh, onto the Kaggle itself. So whenever I say ImageNet dataset, I'll be referring into the ILS VRC data, which was released in 2012 with minor corrections. So the original competition was closed 3 years ago, reason being the performance almost saturated. So, but closure of the competition is not only the end. ImageNet or the ILS-VRC dataset, it is still one of the largest data available to the public for pre-training image models. And also the superset of ImageNet 1K, which is ImageNet 21K, which is essentially the entire data. It is still being used for pre-training large vision models like vision transformers and all. And there was an active workshop in Europe 2021 on ImageNet, which is PPF, past, present, and future. And there are some other large data sets also like MS Coco and Pascal VOC, but yeah, ImageNet is still one of the largest among all of these. And comparing these three data sets with these typical known toy data sets like MNIST, Fashion MNIST, and CIFAR10, like they have a large resolution of images, large number of classes, and large number of samples as well. So yeah, they specifically present real life challenges. So now let's move into the popular computer vision task. Like we will be starting from classification and localization here itself. Okay, so I can say here. So classification means that, okay, I want to classify that, okay, it is a cat. Localization also involves that I'm drawing a box around it. And then we can extend the same definition to object detection setup. In object detection, it is actually object localization kind of thing, but it involves multiple object into same image. Like not only you are limited to one object being classified, you can have multiple, as you can see in this image. The third image, you have two dogs while you just have a one cat. Then extending it further, like we have semantic segmentation. So as we know, semantic means the meaning. So semantic segmentation assigns pixel of same class, same colors. So as you can see for this image itself, the cat image, that all the pixels corresponding to cat are actually outlined in yellow, and the grass on the ground is outlined as green. The trees onto the kind of hilly area uh, kind of colored in a different color, and the sky as blue. So one thing to just notice here is that this is the semantic segmentation, and an extension of semantic segmentation is what we call as instance segmentation. So from an instance segmentation point of view, you can see that, okay, there are two dogs in this image, but both of the dogs are colored differently. So that not only the pixels are provided for each dog, but also a model can get to know that, okay, these are two different dogs. So instance segmentation can have some application in what I say self-driving cars, because you need to classify what are the different objects moving on a road, but not on also you need to keep track of different objects, because if two cars are moving in front of you, each can move in a different direction. Certainly this is very much possible. So yeah, semantic segmentation has some applications in medical domain, like you might need to segment the tumor within the human brain. Classification and localization is kind of a basic task. So yeah, this is how these tasks are actually made. Now let's take a brief upon what are the neural networks and what are the CNNs. So a neural network is a kind of pretty basic idea. It does a series of affine transformation. So by affine I mean it is Wx plus b. So just Wx is what we call as a linear transformation, and shifting it from the origin is what we call as affine transformation. But affine transformation by itself is actually linear in nature. So neural networks try to model complex nonlinear decision boundaries, and for doing that, like each of these affine transforms actually follows a nonlinear activation. We have multiple options for nonlinear activations like sigmoid, softmax, ReLU. Like there is a plethora of activation functions known into the literature. So what neural network actually does, it adjusts the parameters based on the data in a training algorithm to approximate the underlying function or the decision boundary. So the parameters in this case is W and B, and model will try to adjust this so that in order to get the best prediction it can possibly make. So neural network is a universal approximation function or universal function approximation idea is simply that, okay, you can take any vector value data you want and you can establish literally any mapping in theory. And this there is a nice theorem around that also, which is known as universal approximation theorem, and that can easily be seen onto the fully connected network as mentioned in the diagram. So by fully connected, I means that, okay, the input is vector value, the output is also a vector value. Here you can say that, okay, my vector length is 1, so that's why I just have a one unit into the output. And typically what I need to say is that, okay, we have certain hidden layers, and yeah, this one neural network can like for passing the information from the input layer towards the output layer with the hidden layers involved. So number of hidden layers can vary, but in theory, just a single hidden layer suffices. So, and in theory, you should be able to model any like decision boundary using that. So, but in theory, a typical neural network has just single hidden layer, and anything two or more than two hidden layers is what is considered to be deep in theory. But in practice, like I can say that, okay, practitioners have reached a limit of hundred to thousands of layers. So 2 or 3 layer deep network wouldn't be considered deep enough from a practitioner point of view, but in theory it is. So, and there is another a valid reason of like growing depth, because the representation capacity of network grows exponentially with depth. So, and deeper networks, like significantly deeper networks, not like massively deeper networks, like, but yeah, slightly deeper networks are easier to train compared to the very shallow counterparts. And because like there is a pretty analogous series analogy that, okay, different hidden layers can learn different hierarchy of features. So from image classification point of view, I can say that the lower hidden layers will try to capture low level features, and the high level like low level features like edges, corners, these kind of things. And but the higher level hidden layers will try to like capture features like shapes and all. So this is kind of a basic intuition why we should have more than one hidden layers. Then moving on to next, so this is the basic idea of neural network. It is not about CNN. We will be covering CNN to the next slide. But yeah, from a neural net, you can think it like a neural network is nothing but a series of affine transformations or kind of linear transformation with bias. And each transformation follows a activation function. And doing multiple such operations, I can literally model any decision boundary for a classification or a regression task. So now we will be covering into what a convolutional neural network is. So let me just emphasize the fact that fully connected neural networks are basically difficult to train. And this is due to the fact that for image kind of data, that doesn't utilize the spatial locality and stationary statistics property of images. We'll shortly be touching upon what these two are. But yeah, for a vector valued neural network, like any input is independent of the input into the its neighborhood. But that's not the case for images. So this is what where I mean to say that spatial locality does exist in images. Like for example, I can say that, okay, if I'm looking onto a pixel on a race car, if that pixel is red, there is a very high probability that the neighborhood pixel should also be red. And also the one property is stationary statistics of the images, which means that pixel intensity doesn't abruptly change so much. So, but only thing is like if we are using a fully connected neural network, feature at each position in the image needs to be learned separately. So suppose if I'm trying to capture eye detection for a cat or a ear detection for a cat, if the ears only come into the top left position into the training data, a fully connected neural network won't be able to capture a cat for which the image comes out to be inverted and the ear is not on the top left but onto the bottom right. So that's the basic idea. So I can say uh, if I need to draw, like basically since fully connected neural network learn features at different locations. So if a feature at learns for this location, this feature cannot be utilized at this location. So this is the basic idea for that. So what are CNNs? Let's before moving on to what convolutional neural networks are, let's just look into a basic idea of what a convolution operation is. So this is what a convolution operation looks like. I have an input of RGB image. So this is a 6 by 6 image of 3 channels which are RGB. So I can say this is RGB and this is a 6 by 6 channels. Also, I wanted to produce certain channels. So what I have here is like I have two kernels. The number of channels in each of the kernel is equal to the number of input channels, which is three. And so basically, when I try to multiply these three channels with this three kernel, and this three kernel is actually gliding over the entire image. So basically, first it was put here, then it is slided by one location like this way, and so on. Okay, maybe I missed one. So basically, four locations are there. That's why, and you are you are multiplying element wise these three locations with these first three locations, and for the green channel, the second like weights over here. So you get this 4 by 4 output channel. Similarly, multiplying this kernel, you get this channel. So you later on concatenate this entire thing, add a bias into it, and apply a ReLU activation function. You get this kind of representation. So basically, these values are modified using the bias or either the ReLU activation function. And another operation which is of interest is pooling. So pooling tries to reduce the spatial dimensions of an image because like downstream layers of neural network should get lesser dimensional input. Otherwise, they will require a lot of data to be trained. So this is what a max pool does. Like basically, it takes a 2 by 2 window, and for this kind of window, it outputs the maximum value. So this is kind of what a neural network like operation looks like, a convolution looks like. So and so this above we have a convolution operation, and the below you can see how it is being used in a CNN in action. So this is a data image from MNIST dataset, which is dataset of handwritten images. The image is 28 by 28 pixels height and width, and just it is just a grayscale image, so it has one channel. I like it just has a single channel. I am applying a 5 by 5 kernel. So as you can see, the here I can see that okay, I'm applying a 3 by 3 kernel or a 6 by 6 image. So you can calculate the output dimension as 6 minus 3 plus 1, which comes out to be 4, certainly in this case. So here you can see that 28 minus 5 plus 1, it comes out to be 24. Then I'm applying a max pool of 2 by 2, so I'm getting a 12 by 12. Number of channels are being changed. So originally I have one channel, now I have n1 channel. Just to mention that max pooling doesn't take the number of change the number of channels. Then again we are applying a 5 by 5 kernel. So 12 minus 5 plus 1, it comes out to be 8. Again applying a similar max pooling, we get this kind of thing. And at any point of time when I believe that my spatial dimensions are significantly reduced, I can translate this kind of output, which is a 3D matrix or a 3D tensor, into a vector by using a simple flattening operation, and then can similarly apply a fully connected neural network on top of it. So this kind of approach is typically used to do two things. First of all, at first place, it reduces the size of the vector, because if I'm seeing this kind of thing, if I'm inputting this thing into a neural network, I'll be getting 28 by 26, which is 786 I get, or approximately 700. So this is not 786. It has to be a different number, but not sure. Yeah. Then, but also another case is this, that these convolution weights which are being learned, these kernel weights, they try to learn the same feature across different position in image. So if one feature is being learned at single position, during that for some other data point, the same feature can be applied at a different position. In terms of representation capacity, I need to mention that okay, CNNs are actually a subset of fully connected network. Reason being pretty simpler, that a fully connected network can try to like map these two pixels together in the very first layer. That is certainly possible for a fully connected network, but not for a CNN. But CNNs assume these properties of an image, which is a spatial locality and a stationary stats, and this reduces the amount of training data required. And yeah, we have already discussed, and this the CNN kind of setup, along with the limited training data we have, it enables us to train deep neural networks. So experimentally, I've also seen it that okay, for 3 to 4 layers deep fully connected networks, it is quite difficult to train them for a very good like accuracy using any of the standard data, like be it a MNIST or a C410 kind of thing. So CNN does a feature extraction. We have discussed this itself. What convolution operation performs like gets us an output is feature maps. So basically these are feature maps. This is my feature map 1, this is my feature map 2. So these are the feature maps which a convolution operation performs, like gets me into the output. And so basically they are reduced into the spatial dimension and later on can be vectorized to be fed into a fully connected layers. CNN are kind of suitable for the data which have a spatial locality in stationary stats as discussed. So they can also be the same idea of convolution can be extended into from 2D to 3D or 1D images. Like we don't have 1D images at hand, but yeah, some of the 1D data which satisfy some of the spatial properties can be an NLP statement, a text statement, or a signal, because like signals also doesn't change abruptly that much. And CNN allows us to do parallel processing. So suppose if I'm using a GPU and I have a multi-core setup, then like suppose let's just suppose for cores for example now. So convolutions on this part can be done in one GPU. This on second, not one GPU, one core, second core, third core, and fourth core. So yeah, convolutional neural networks are highly they have a good parallel capacity, which can be utilized onto modern hardware like GPU. So by now we have covered a brief introduction of what fully connected neural networks are, what are convolutional neural networks and all. Let's move into the AlexNet, which was the first CNN architecture which gets the state-of-art performance. So onto the ImageNet data. So and this is the common format I will be using into like discussing the literature details. So yeah, this paper was published in June 2012, and like this was the paper title. The lead author was Alex on like, and hence it is called the AlexNet, and under the guidance of Jeffrey Hinton at the University of Toronto. This was the first GPU implementation of a convolutional neural networks. This is the hardware specifically. Like they just used 6 GB of GPU, and it took 5 to 6 days for them to train. So their top 5% error rate on this ImageNet data, which is ILS VRC 2012 data, was 15.3. The second person in this competition, the second model in this competition was not a neural network approach, and they have a top 5% error rate of 26.2. Certainly, you can see that there is a large difference among these two. And just to mention what top 5% is, like top 5 error case, like I have my 1,000 classes, so I sort them out. So I can say that okay, they are in increasing order of probability, and these are my top 5 values. Um, if my correct prediction lies in any of these 5, I can say that okay, I am correct. Otherwise, if it doesn't lie in these top 5, I can say that okay, it is incorrect. So top 5 error rate is what is being used to evaluate the models. But certainly, if you wanted to be exactly accurate, you can take top 1. So yeah, but this was the top 1 error rate or top 5 error rate of AlexNet. And actually, this model implemented for the first time a CNN onto GPU, and it also compiled many of the techniques that were actually known at that time for neural networks. But the most useful being the CNN inductive bias. So what was CNN inductive bias? We have already discussed CNN inductive bias into the previous slides. This is the CNN inductive bias, like spatial locality and stationary stats. So like onto any of the application where you can throw a CNN at, and the properties of input data are kind of suitable for a CNN to be applied. This is what we call as like CNN has an inductive bias. Like, okay, I should start with a CNN. That's the basic idea. So moving on to the network details, AlexNet has 5 convolutional layers. So 2D convolutional layer, which we have already discussed, followed by 2 dense hidden layers and a final dense layer, which has a 1,000-way softmax on top of it. So the output vector is of 1,000 length, and a softmax is being applied. This entire model has a 60 million parameters at that point of time. And so actually, along with these convolution kind of operations, ReLU was used as a nonlinear activation function, and also a normalization technique, which was not used in all layers. It was used in first and second convolution layer. And this is known as layer response normalization. This was actually being used. Okay, so we'll slightly be touching upon what layer response normalization is. And also overlap pooling was used in this architecture. So earlier onto the slide, we have seen, okay, a 2x2 max pooling, right? And you can see that, okay, not only 2x2 max pooling, but these pooling windows are non-overlapping kind of in nature. and this you can see also from the color coding. But AlexNet doesn't did it. They actually used a 3 by 3 max pooling with a window size of 2. So I can say that okay, like they are using kind of this kind of window, but then they are shifting it here. Like I can say the sizes boxes are of same size. It is just me who has drawn it them off to be different size. But yeah, so this is the stride size of 2. My kernel has shifted 2 locations at once. So this kind of overlap pooling was used. A dropout of 0.5, which is 50% of the units were dropped for the dense hidden layers, not for any convolution layer or not for the final classification layer, because that won't make sense. And considering this kind of scenario, as you can see that there are dense layers, then you have the output layers. So actually less than 5% of the parameters were contained into the convolution layers. So I can say that okay, CNN inductive bias was actually being used, but still the number of parameters which actually lie in the CNN layers are quite less. And CNNs also they are being attributed for lesser number of parameters, as you can see here, because like we have already discussed that same feature would be learned like can be applied at different locations. So you won't be requiring different set of parameters for each location, and this is how CNNs typically reduce number of parameters. And for due to this reason, only 5% of the parameters were lying in the these first 5 convolutional layers. Some of the other niche details were which were like not every layer communicates with each previous layer in a AlexNet kind of setup, because it was implemented in 2 GPU, and we will also be seeing this within a figure. But the final submission towards the competition was not a single CNN. It was actually a 7 CNN setup where 5 CNNs were trained on the original data, which is ImageNet 1K, and 2 CNNs were actually pre-trained on the entire ImageNet data, which is ImageNet 21K, and later on fine-tuned onto this ImageNet 1K data. And these 2 CNNs, which were pre-trained on ImageNet 21K, they have 6 convolutional layers, not 5. So this is kind of some internal detail I can say from the paper. And actually, this full ImageNet 21K data, which is actually it is 1.1 terabyte in size. So this was in use for pre-training from 2012 itself. So this is kind of a model architecture for the AlexNet. I have an input image. Let's just not go into the architecture. Let's discuss what is being here. Okay, so the data pre-processing is quite simple. You rescale the image so that the smaller edge has a size of 256 pixels. Then you take a center crop of 256 by 256 and a channel-wise mean subtraction. So let's discuss what this means. ImageNet images are all not of same size and same aspect ratio. So suppose this is one of my image. I'd resize it in such a way that okay, this boundary, the smaller edge, is 256 pixels wide, and proportionally it can go anything like just depending upon the aspect ratio. Then what I'm doing is I'm taking a center crop. So I'm taking this center crop of 256 by 256, and from this crop specifically what I'm doing is that I'm subtracting the channel wise mean. So if x is my pixel value, depending upon whether it is R, G or B, I need to subtract this channel mean. So it can be red, it can be green, it can be blue. It entirely depends like whether this x value is coming from which of the channel. So yeah, this is one thing. And certainly from the data pre-processing thing, you can see that okay, this information is never used. So only center crops are being used, and assuming that okay, most of the information you required for classification is lying in center part, but this information was never used. So there is an information discarding kind of thing going on here, and this is not a good idea. Like you should be using the entire information available if possible. The batch size was 128 images, not 128 images of 256 by 256, and I'll be mentioning into that, like going into that. The moment optimizer was SGD with momentum of 0.9 and a weight decay of 5 into 10 raised to power minus 4. And these weight decays kind of thing we rarely see in practice when creating neural networks, but weight decay are in constant use for the entire ImageNet literature. An initial learning rate of 0.01 was used, and it was decreased using the validation set for approximately 90 epochs. So when I say how it is decreased using validation set, like suppose your performance saturates, like first it drops, then it saturates. So at this point of time, I decrease my learning rate. Performance goes like this, then and then. Okay, so in AlexNet training, the performance learning rate was decreased thrice. So it is 1 and 2 and 3. And finally, the training stops at approximately 90 epochs. So actually, the training was conducting based on iterations, but yeah, we can estimate that thing in terms of epochs. So this is what it is. The weights were initialized from a normal distribution of 0 mean and 0.01 standard deviation. And not all layers, but yeah, second, fourth, and fifth convolutional layer bias was initialized to 1 to help ReLU activation function, because we know that with ReLU we have a dead ReLU problem. So for any values where x lies in this region, ReLU is actually dead. There is no gradient, so you can't learn anything. So due to that reason, the second, fourth, and fifth convolutional layers have actually bias set to be 1. So this is data preprocessing, not the training data generation. Let's move into what training data generation is. So as you can recall, we have a 256 by 256 size of a square patch. Let's redraw it here. What for training specifically, I'm taking a 224 by 224 patch out of this larger patch, and it can be taken randomly anywhere. It can go like that. It can go like that. It can also be in center. Okay, but randomly anywhere, literally. And also not only this random 224 by 224 patch can be taken, but it can be horizontally flipped. So horizontal flip is just a mirror flip. And also color can be changed via color jitter. So color jitter is a basic technique which was mentioned in paper. We won't be discussing here itself. So this is training data generation. Now let's look into what model is. So as you can see, the training images are actually of size 224 by 224. So here we have 224 by 224 images, and I won't be repeating numbers twice. So let's say it is 224. We are applying a 11 by 11 kernel, okay, with a stride size of 4, as you can see here. And this 3 is actually the number of channels, which is RGB images. Okay, so using this calculation, what we have obtained is like we have obtained a 55 by 55 image with 48 channels, and 48 channels on one GPU and 48 channels on other GPU. So basically this path corresponds to GPU 1 up till here, and this path, the second part, corresponds to GPU 2. So this is part of GPU 1. Okay, so onto this image, which is of 55 by 55, we again apply a 5 by 5 kernel, and we get, also there is a max pooling involved in between. So using that, we get a 27 by 27 window, and 27 by 27 sized feature map. Now we have 256 channels, 128 in one GPU, 128 in another GPU. As you can see, the channels which are like obtained at first GPU, they are only using the input, like calculation which was being done in first GPU, and same goes for the second GPU. Like, so there is no cross GPU information sharing, but there is an instance where the cross GPU information sharing was taken place. So yeah, into the third convolutional layer, you can say that okay, my image size is reduced to 13 by 13, but I'm for calculating any channel into either of these two, I'm using all the input channels from the from different GPUs, like from my own GPU and also the other GPU. So this is one of the only instance where the information sharing was used for the CNN output feature maps. Then it again goes exclusive to each GPU. After that, we vectorize the entire data and calculate two hidden layers on top of it. So then these vectors are not actually of 2048 dimensionality, but 2048 on both, what I say, both GPUs. So it is 4096 each, and a fully connected layer of size 1000 and after that you apply a softmax. So this is what typical information flows look like in AlexNet architecture. So as you can see that earlier the GPU, like GPU bandwidth, like cross GPU bandwidth was not that high. So yeah, the authors typically reduced the communication between two GPUs. So this is how the training data was generated. So this 224 by 224 patch was randomly taken from this original center crop patch, which we have already discussed, and there is information discarding into this part. Then for the testing thing, the authors have used a 10-way crop augmentation. This is a fairly standard practice. We will see it time and time again. So let's see what it is. So suppose this is your original image, which is size. We know the size. It is 256 by 256. So what is the 10-way? So let's assume this is my patch 1. Then this is my patch 2. This is my patch 3. Then this is my patch 4. Then I also have another patch 5, which is lying at the center. So I can say the 5 patches are top left, top right, bottom left, bottom right, and center. So these are my 5 patches. I can say 5-way multiplied by 2. What is 2? 2 denotes for horizontal flipping. So for each of the patch, like if image is looking like this, I also obtain a patch like that. So this way we get a 10-way data. So actually the prediction was made on these 10 patches, and the average output value of the softmax was used for the final prediction part. So whenever into the future literature we see that okay, this is the validation set performance or the performance onto the ImageNet data, we will be referring to this 10-way augmentation most of the time. Okay, and single crop augmentation was separately is actually separately discussed, where most of the focus is on central crop only. So this is what AlexNet is. Like we have briefly touched upon the model architecture, the training procedures, how the data is generated, and also we have discussed that okay, there is a case where data is being discarded. We have also discussed like what kind of model architecture is there. Just to mention that okay, this is the normalization technique which was being used by the paper. This is what we call as layer response normalization. You can look for it later, but yeah, it is almost of no use into the model architectures. And what it typically try to do is that okay, as you can see that x and y are spatial dimensions. So x and y refers to a position and I refers to a channel. So for any channel at any position x comma y, what I try to do is I try to sum up. Let's take for simplicity, let's take k equal to 0, alpha equal to 1, beta equal to 1. Like basically these are typical hyperparameters of layer response normalization. Let's take these kind of simplistic values. So what I'm trying to do here is I am dividing the actual value by the value of squared, like different squared values of what. J is considered like taken to be max of 0 and uh, it is j minus n by 2. So j is basically the channel index. As you can see here, it is channel index. So for some channels before this channels and n by 2 channels after it, I am taking an average of it. So like if any of the channels which are after and before my current channel, these values will be squared out, like squared, everything would be summed up and divided by my actual value. So the author states that okay, this kind of normalization tries to create a competition among the different channels. That okay, if one channel is coming out to be high and other two channels are coming out to be low. So after the gradient adjustment, these channels also should come out to be high. So this is what this layer response normalization kind of should motivate it. Uh, Only one case which I can possibly think of is that layer response normalization is one thing which shouldn't be applied to a biological neural network, like kind of a mammalian brain. Reason being fairly simple that okay, this kind of competition shouldn't be the case in biological neurons. Otherwise, like maybe some of you might not know, but yeah, biological neurons do fry up. So like if you are excessively using a neuron, they might die. So and also if you are not using a neural like a brain within a like a neuron with a human brain, like your brain might repurpose it for some other task. So yeah, uh, having an excess usage of some neurons and having absolute zero usage of neurons, both two are not healthy from a biological perspective. But yeah, so this kind of normalization was only see like we will only see this in AlexNet paper. Down the line it won't be there. So let's discuss in what are the contributions which paper had done. So first of all, they implemented for the first time a CNN on a GPU. So they also applied some of the regularization techniques. So they used dropout. So dropout is specifically prevented overfitting, but it actually doubled the iterations for convergence. So when I say convergence, I mean to say the convergence of loss function onto the training data. So without using dropout, you can converge in half the iterations, but only thing is that your model will be overfitting. So yeah, I can say that, okay, dropout is essential to this network. Then layer response normalization gets us to 2% generalization performance. So which is like 2% reduction into the top 5 error rate. 1% generalization gain was attributed to the training data augmentation. Training data augmentation we have seen already, which is what I say is this. I'm taking a random crop of 224 from this, and also horizontal flip and color jitter. So yeah, that's this is what it is. Then coming to, there is a slight analysis which was also done by the authors. Like they try to like visualize the texture and colors which are being learned by the kernels. So as you can see, there is certain some visualization here. Let's see what this visualization is. So as you can see that there are 11 by 11 sized kernels which were being used, and 96 channels are being produced, 48 on one GPU and 48 on another. So these channels are nothing but it corresponds to the exact same thing. So like I can count for a moment that, okay, here I have 4, then here I have another 4, then another 4 and another 4. Okay, so 16 filters in one. So 16, 3, 48. So 48 over here and then 48 here again. So author also mentioned that like noticed that since not all layers communicate with all layers, so across different random initialization, one of the GPU, like either one of the GPU tends to learn kernels which are more biased towards the texture, while the other GPU learns some kernels which are more focused onto the color aspects. Then author also does some analysis on around like what kind of different cases the model is failing onto and how embeddings of these models can be visualized. So let's look into some of the cases where how model is working. So as you can see for these 10 images, for the this image like 1, 2, 3, 4, 5, and 6, the model is working perfectly fine. For this image, the actual label was given as grill. So, but and also for this image, the actual label was given as to be cherry, but that is not the case. Now the model is predicting highly with very high probability that, okay, this is a convertible, and convertible has a more probability than grill. And like for this image, model is predicting that, okay, it is a Dalmatian dog and not a cherry. So certainly you can see that this is an issue of mislabeling by the human annotators. As you can see for this image, this much reasons actually has cherry in it, but a larger area of this image, or at least this part, can be attributed to a Dalmatian dog. So yeah, this is one of the reasons that, okay, for these kind of images, model is not performing well. Similar goes for this, that, okay, here I have a grill, but the entire picture actually represents a convertible car. So model should have a higher probability for convertible instead of grill. So what author does is like they attribute the fail cases to the poor quality of dataset, the poor labeling within the dataset. And now looking from an embedding point of view, so what authors have done is that they said that this AlexNet kind of setup can be used for image similarity search. And how it can be done is that considering this model architecture, so before your classification, you have this 4096 sized vector, which is 2048 from each GPU. What we can do is like for all the training data sets, we can take these embedding vectors and like we can cluster them, or for a new image which is coming into the picture, we can do a image similarity search, a k nearest neighbor kind of thing. But one certain issue would be the case that 409 like 96 is quite high dimensional vector. It is pretty high dimensional vector, and knn onto this data like won't be a good idea. So one approach which author suggested is that at least this 4096 sized vector is capturing some of the semantic information. So what we can do is like we can like compress this 4096 length of vector into some lower dimensionals, say 128. And using what? We can use the autoencoder to like compress this embeddings, so that like now similarity search can be performed into this low dimensional vector. And this is better than deploying autoencoder onto the original image itself, because these vectors actually have some information around the classes, and a pure autoencoder won't be having something similar. So my comments onto this paper is that okay, CNN does some feature extraction for the image data and had some potentials for the future work. So this is the base idea of AlexNet, what AlexNet is, like on what kind of images it is not performing well, like how different kernels are being visualized, like for kind of a basic interpretation point of view. And we have already discussed the training and testing data generation process and training setups and all model architectures and almost everything. So now coming to another paper, which is network in network. So network is not a paper from the ImageNet literature. The paper doesn't have any experiments onto the ImageNet dataset, but the approach was quite unique. So this paper was released in December 2012 uh, from University of Singapore. It actually achieved state-of-art performance on not ImageNet, but on CFER dataset, CFER 10 and CFER 100. SVHN, which is Street View Housing Number, it can be seen as a complex MNIST, but a real life MNIST, where I can say, and the original MNIST dataset. So what this paper does is they actually question the linear behavior of a large kernel for feature extraction and replace that large like linear behavior, like linearly behaving large kernel from a universal approximator. We will soon be seeing what it is. So, but what they have replaced is like basically they have replaced a large convolutional kernel with a universal approximator, and their universal approximator actually can be like exactly approximated, not approximated. I shouldn't be mentioning approximated, but I should say it is equivalent and can be designed using some spatial kernels. So when I say spatial kernel, it is a kernel of any size, but not one by one, followed by some one by one convolution. So what these paper does is like the contribution of paper goes like this. They have three MLP conv layers. So MLP is multi-layer perceptron. So they have three MLP conv layer, each follows max pool, and the final layer follows global average pooling. So yeah, like from my point of view, like this is the first paper which mentions about global average pooling, and this is actually being used heavily in modern architectures. So the paper doesn't mention anything about normalization and activation function, but I can safely assume that ReLU is being used. And like since the network is just 3 layers deep, so I'm not assuming any normalization technique being used here. MLP conv layers follows a 2 by 2 max pool, which I've already mentioned while I was like reading through the first point. But these 2 by 2 max pools were used with a stride size of 2. So this is kind of similar to the behavior we have seen here. Like this is kind of a 2 by 2 max pool with a stride size of 2. So dropout was actually used in all of the layers, but not the last layer, because last layer was actually used directly for the final classification. So there is no point of using dropout into it. So this is what MLP conv layer look like. So first just look into a basic data pre-processing like the way we have looked for AlexNet. So all the data pre-processing and training details were actually taken by Max Out Network. So this was one paper from Ian Goodfellow. We will be covering it into the details later on. But two things to mention, like because this paper of network in network typically mentions a lot, is that the ZCA whitening and the global contrast normalization was used for image processing. I'm just assuming that okay, these are some image processing techniques. Let's move from this. So the role of contribution is that first of all, they are using global average pooling. So this kind of like let's look at it from a model architecture point of view. So this is a basic convolution operation. So this is your input image, your input channel. So this is your input channel, this is your output channel, and this is basically a kernel. And what is the size of this kernel? The size of this kernel says 11 by 11, which is the case for ResNet. The author says that okay, the values which are being used here, which is like say X, and the kernel weights which are here, like say W. So this single value which I am obtaining is nothing but W transpose X. And since these two are vectors, so I can say that okay, this is my W, this is my X, and I'm just getting a single value. Only thing is that with respect to these multiple pixels, and the number of pixels would be the same as the size of this vector, which is like nothing but 11 square. So for these 121 pixels, you are assuming that okay, this behavior is linear. The feature extraction has to be linear, and this is the same formula for linear. Like we see linear behaviors like this, right? So basically, you are taking this expression long enough, and like you can say that okay, I have from x1 till x121, and I'm applying certain weights. So basically, this is kind of a very long linear relationship. The author claims that okay, instead of using a linear large kernel, why don't we do something like that? That on top of this linear kernel, I apply some fully connected layers so that a complex non-linear relationship can be learned before I translate this channel into this channel. So this is the basic idea. And the model architecture was pretty simple because the data sets were simpler. All of the data sets like C for 10 and C for 100, they were all 32 of 32. SVHN, which is Street View Housing Number, this is also 32, and MNIST is 28. So you can what you can simply do is like you can pad certain pixels around MNIST and you can also make it 32 by 32. So this is the basic model architecture. So here your image size is 32. After this operation, you also does a max pool. So here your image size is 16. Then here your image size is 8, and this is how it goes, like 32, then it is 8, it is 16, then it is 8, and then after that it would be 4. But let's not just mention 4 over here because these channels were directly like mapped to the single values using the global average pooling. So this operation here, it signifies the global average pooling. So basically what I'm doing is like I'm taking the average of all the pixel values. And what would be the number of channels here is like each channel corresponds to one class. So the number of channels into the final output would be the number of classes. So except for C for 100 dataset, for SVHN, MNIST, and C for 10, the number of channels would be 10. And only issue with this model architecture is that your number of channels actually would be dependent on the number of classes. But yeah, there are certainly benefits to using global average pooling. Like first of all, the model is robust in image translation. Like no matter whether you translate some image slightly to the right or left, or you rotate it entirely, the average pooling won't work, right? Like won't change the results because you are taking a global average. And also there is no dense layer present at all, like not even a single dense layer. So the model has far lesser parameters, and like model is less prone to overfitting. Then what was the analysis done by authors onto it? Like basically author tried to visualize the activity for each class image, and also the location corresponds to the actual class. So as you can see that okay, these are some images. Like I can certainly see that okay, this is a car, okay, this is a plane, actually this is a car, then this is a cat, this is a dog. So certainly I can say that okay, for cat, here is the location where the face of my cat lies. So for this class, which is actually corresponds to the class, as you can see, the activity is in top left, which corresponds to the face of the cat. And for all the different classes, the activity is quite next to 0. And the same goes for other classes. So this was actually visualized that okay, the activity was highest for the corresponding class. So which says that okay, this is using something. Only thing is that uh, this kind of architecture can be easily like created in any of the modern deep learning framework, like be it Keras or TensorFlow. As you can see that okay, this layer is a large kernel, which is 11 by 11 kernel, but these two layers can be easily approximated using one by, like not approximated, but yeah, they are equivalent to using one by one convolution. So yeah, this is what network in network is like. And my comments onto it that okay, large kernel which were used in AlexNet, they are actually bad due to the linear assumption. So at least what this paper comments is that these large kernels are bad due to the linear assumption. And we will also be seeing another paper today, which is VGG. It is quite a popular architecture, and VGG networks are heavily used into the transfer learning setup. But yeah, VGG architectures also does highlights another issue along with the linear assumption of the large convolutional kernels. And in modern neural networks or model CNNs, these large convolutional kernels are not being used. So let's just now discuss the one fact that okay, this basically this part of the MLP conf can be approximated using a one-by-one convolution. So to highlight this notion, let's take an example over here. Okay, let me draw here itself. So suppose this is your large image. So I am assuming a size of 11 by 11. I'm multiplying this by 11 by 11 weight value. So this is my X and this is my weight. I'm not using a single weight. There are multiple such weights, each producing a different channel. And for simplicity, let's assume that image is just of a single channel. So it is a RGB image, not a RGB image, but a grayscale image. So it is just a single channel. Then, so this is a convolution operation. Okay, so this is where I'm doing a convolution operation. Suppose I'm getting different such weights. So I'll be getting different channels, and I can say that, okay, different channels, like say, for example, suppose I have 256 channels here. Certainly, you can see that if the size of my convolutional kernel and the size of my images are absolutely same, then I would be getting a single value only, right? Then what I typically do is, like, and apply a one by one convolution on top of it. So these are not 256 different values; these are 256 channels. Okay. On top of it, I apply a ReLU. So basically, this is how I removed the linear component of this thing. And after ReLU, I again like applied a one by one convolution. So, but different one by one convolution. So suppose 512. So this is the size. Okay. So 256 was the input size. Then one by one is size of convolutional kernel. Then I'm trying to produce 512 channels out into the output. So this is my like dimension of the convolutional tensor. Then what I'm convolving it with, like I have a one by one sized but 256 input. So this is my input. This is my kernel. What I will get as an output is that I'll be getting like typically one by one by 512. So basically what I'm getting out of it is that now I'm getting 512 channels, and but I'm just not getting these 512 channels with without linearity. Yeah, like with linearity, now I also have a non-linearity involved in between. So this is the basic idea, and you can see, like, with a smaller example, that suppose let's just take a 3 by 3 input, and I'm applying a 2 by 2 kernel on top of that. So one location can be this, then second would be here, third goes here, and fourth goes here. So if I'm creating a convolution, it will give me a result of this thing. Okay. So, and applying one by one convolutions at this place. So I'm just taking one weight here, and that same weight is being shared in this these four different parts. So using a one by one convolution, I will just be getting the same size output. But yeah, the number of channels would be different. So for this part, I can have 256 channels. For this, I will have 512 channels without changing the spatial dimension. But also this will include a ReLU in between. So nonlinear relationships can be captured easily using this network and network kind of approach, which was not possible like using the larger kernel at the very first place. So it allows us to model some of the non-linearity, but yeah, still the linear part which was done by this large kernel, which is 11 by 11, it is actually still there. So that still needs to be removed. But like what we have discussed so far is that we can easily implement this network and network architecture using these one by one convolution, and global average pooling is part of all of the modern deep learning frameworks like Keras and PyTorch. So yeah, that can be pretty much implemented. Now we will be looking into the VGG architecture, which is quite popular. So this architecture comes from a lab, which is Visual Geometry Group. It is a lab within Oxford University. And this paper was published in 2014. The paper didn't won the first position into the competition, but they were actually they stood second, and the Google Linux, which is another architecture, stood first. The architecture was implemented on Ford NVIDIA Titan Black GPU, and the training took 2 to 3 weeks. So I would like to highlight this thing that okay, the AlexNet took 5 to 6 days on a 2 GPU setup, and also the 2 GPU or NVIDIA 580, like NVIDIA GTX 580, which is quite lesser compute compared to the compute effort which was being put by the VGA architecture. So this is one thing that you need to keep in mind, like moving forward, that networks will be becoming more and more complex. The performance prediction for VGG was less than 5%, less than 5%, or less than not 5, less than 7% of top 5 error. If you can recall, for AlexNet, it was approximately 15%. So as you can see that, okay, approximately half of the error is reduced from AlexNet to VGG within 2 years. Google Linux is also known as Inception V1. So there are different versions of Inception after that, but yeah, it was the first Inception architecture. So VG is slightly like marginally actually like perform poorer than the Google Linux. But Google Linux actually has two issues within it. Like first of all, the model architecture was quite complex comparing with the VGG, and also they have aggressive downsampling. And this aggressive downsampling is not a good idea. We will also be looking this thing while discussing ResNet architecture. So one thing just to mention is that this inception kind of models would be highly complex. So it is slightly lesser chance that we will be covering the inception series of models, like be it inception V1 or V2, V3, V4, and the core idea of VGG is to use the smaller convolutions, which is 3 by 3 convolutions, and increase the depth. Okay, this allows for a state of art performance not only for the ImageNet, but allows for a state of performance in the state of art performance in transfer learning setup. So the authors of this paper claims that okay, the representation which were actually being learned by this model, they are generalizable to the different tasks. So how they typically use the 3 by 3 convolution is, let's see that. For example, like I won't be using uh, 2D convolutions. For simplicity, I'll be using 1D convolution. So suppose you have a convolution of size 5 by 5. How can I model this convolution using a 3 by 3? So suppose I'm taking first 3 by 3 convolutional layer. Okay, this is my first layer. So it can be applied at this position, then it can be applied at this position, then the same convolution can be applied at this position, right? This way, my output would be a 3 by 3, like 3 length vector. Originally, my input also has to be like 5 length vector. Okay, and just to mention, this is my x, this is my kernel dash, which I'm like k dash, which I'm trying to approximate. This is my first kernel, which is k1, and the output would be like of this k1, which would be x dash, and applying another 3 by 3 kernel, which is k2, I'll be getting a single value. Like multiplying these element wise and adding them finally get me the output value y. And this can be simply done by using these direct multiplications onto a larger kernel. So what is the benefit of using a smaller kernel, like multiple smaller kernels over a single large kernel? Like one direct benefit in the case of 2D convolution is, like instead of using if I'm using a 5 by 5 convolution, so I'll have 5 square parameters, which is 25 parameters. But in the later case, I'm using 2 of 3 square, which is 18. So this is parameter reduction. And certainly what I can claim is that, like, you can check this for yourself, but a 7 by 7 convolution can be actually implemented using 3 by 3 convolutions. So here you have 49 parameters, but here you just have 27. So yeah, so smaller convolutions, when applied multiple over each other, they not only allows for lesser number of parameters, but also one thing which we have discussed in an earlier paper, which was network in network. After each of these smaller convolution, you can add your nonlinearity. So you can add RLU here. Then onto the final output, you can also do RLU here. So with the same 5 by 5, like with the same receptive field. So by receptive field, I mean to say that, okay, the size, the area or the size of the image which you are trying to locate. Like now you have two nonlinearity, but in the original larger kernel, not only you will have large number of parameters, but you will also you will only be able to use one ReLU. So yeah, even more complex nonlinear relationships can be modeled, and also with a lesser number of parameters. So lesser parameters allows us to have more generalizable model, because lesser the parameters, lesser it is prone to overfitting. And also the representations can be quite complex because you have more non-linearities involved. So network details are pretty simple. All convolution operations which I mentioned as weight layer, ReLU follows them. There was no normalization method used explicitly into this architecture, not even batch norm, because batch norm was invented after the VGE paper, not before that. Layer response normalization from the AlexNet, actually the authors tried it, but that didn't result into model any performance improvement. So they typically drop the layer response normalization. Then, but still there is a claim that okay, authors were able to train 19 layers deep network. If you can recall from the AlexNet is just 5 convolutional layers and 3 layers on top of it, 2 hidden and 1 final layer. So AlexNet is just 8 layers deep network. And if they require 3 LRN layers, layer response normalization layer, how these papers, like these authors were able to train a 19-layer deep model, which is VGG 910, without any normalization at all. So there is a hack around for that. We will see that. And these kind of details were actually missing from like multiple courses and books. So yeah, that's one thing we'll be covering from the core paper itself. The pooling was not also overlap pooling. The paper was just using a 2x2 max pool with a stride of 2. This is kind of similar to network in network paper, but different from what AlexNet people are using. Dropout was same, like 50% dropout within the hidden dense layers. Most parameters are still in the fully connected layers, like we will be seeing this. Then other detail is that the final evaluation for this competition, which is ImageNet 20 ImageNet competition, like author just submitted a ensemble of VGE 16 and VGE 19, which are respectively 16 layer and 19 layer deep VGE architecture. So if you can also compare that with respect to AlexNet author submitted 7 or like ensemble of 7 AlexNet models. And also one thing to mention is that even when Google Linet outperformed VGG slightly, single model performance of VGG is actually better than single model performance of Google Linet, which is Inception V1. And not only this, like VGG typically, like VGG into the final submission submitted 2 models for the final like scoring. Google Linet actually submitted 5 models. So this is another one of the reason that why Inception V1 won the competition, but VGG we can see that okay, with respect to single model performance, and also it is kind of better. So now we will look into like how these authors were able to train deeper models, and also we will pictorially look into the model architecture. So data pre-processing, coming to the like entire data pre-processing is kind of similar. Only thing is that I'm not resizing this image to 256 size. Okay, this is not the case now. I'm now resizing this image to a size S, where S lies uniformly. It can be taken anything from 256 to 512. That's one thing around the resizing part. So you will get like same image but at different scales. And not only that, the final patch which we are taking, so that will actually be taken across the entire data. Unlike the AlexNet where we are just taking the center aspect, like center crop, now you can take patch across the entire image. So yeah, uh, VGE paper actually better utilize that ImageNet data itself. The batch size was slightly increased from 126 to 256. They are also using 4 GPUs. The SGD, which is optimizer, so optimizer settings are kind of same. SGD momentum with 0.9 of the momentum value. Then weight decay was same. Learning rate was again same. The learning rate was decreased thrice. I guess for AlexNet it is twice, but we can check this from the paper itself. And the training was roughly done for 74 epochs. Weights were actually initialized from the same distribution from which AlexNet weights were initialized. But at this point of time, the Glorot weight initialization, which we also popularly used in model architecture, like modern frameworks and all. So this paper was already published. Only thing is that VGG authors were not aware of it. So now the thing is this, like one hack around which we already discussed into the last slide, which we mentioned, actually not discussed, that okay, there is a hack around to train deeper models. So this is that hack around, that okay, additional layers were added into the trained model to avoid vanishing and exploding gradient of randomly deep models. Simply I can say that suppose you have a 4-layer deep network. So you train, like I'm just taking an example. You train this 4-layer deep network. Now you wanted to create a better, more deeper network. So you insert some layers in between. So now you have a 7-layer deep network. These four layers are originally trained, but these 3 layers are inserted new. Now you train this entire network. Once this is trained, you can insert some other layers as well. So this is the trick, and this is how they basically trained deeper networks using the shallower pre-trained networks itself. And also the model was first trained to the crop size of 224 by 224. Later on, not crop size of 224, but originally this size was taken to be 224. Then this size was taken to be, which I have mentioned here, that okay, it is randomly taken from this. Actually, it is not the case. Originally the size was taken from 224. Then these images were resized to a size of 384, and finally the images for the third training, they were like taken from this random rescaling. So random crop of the same size, 224 and 224, like this is spatial dimension. The square patches were taken from the entire images. So not like center crop of AlexNet, we have discussed this. The same data augmentation follows from the AlexNet. Okay, the horizontal flip and the color jitter. So color jitter kind of adjusts the color. You can independently read about it. But yeah, so this is how the training was done. Only thing is that VGA paper method, like authors mentioned that you can't just directly train this multi-scale network. Where like otherwise, at the very beginning of the model training, you will see images of different size. So you should start with a smaller size network, then like increase the scale and finally apply a multi-scale algorithm. And even before doing that, you should do this thing. Like start with a smaller network with this initial 224 size and grow the model specifically like to the desired size, and then go for this large scale, like large image scale training and multi-scale training. So this is the basic explanation of VGG architecture. Like you can visualize this as such, like originally I have this RGB image, then like we are obtaining some channels out of it, which is 224, 224 and 64. So two channels. Then we have a max pool. So red color here denotes the max pooling part. Then we have 2 channels. Then we have a max pool. Then we have three convolution operations, not 3 channels, but 3 convolution operations. So here there are also 2 convolution operation and 2 convo layers. Then max layers, max pool layer, then 3 convolutions, then max pool, 3 convo, then final max pool. And these are the dense layers followed by the softmax output. So first of all, the basic philosophy of this VGG architecture was also utilized in many popular architectures down the line, like ResNet and EfficientNet and whatnot. So let's see why this kind of like resizing using the max pool is done. And not only like max pool is evidently clear that okay, you want to reduce the spatial dimension of the size. But why these number of channels are being increased? Like originally you have 64, then you have 128, then you have 256, and you have 512. So why that's the case? So suppose your original image is of size, let's let's say 256 is my input channel. Now my original image size is, let's say, 56 by 56. Okay. And now I'm trying to produce 512 channels. Okay. I'm taking example of, like, I should say this one, like something. Okay. No, not exactly. Let me take a pause over here. Like, okay, I'm using, like, basically I'm trying to show the calculation for this one. So this shouldn't be 512, this should also be 256. Okay, now let's just compare the compute that is being done here with compute at this point. So at this point, compute would be 28 by 28, but here you have output channel says 512 and input channel is 512. So certainly what you can see is that this number is actually doubled. So these two numbers are doubled, number of input output channels, but the spatial dimensions are actually divided by 2. So what I can say is that not only the compute requirement across different layers, but also number of parameters across different layers would be same. So this is the basic philosophy, and you can also like take a natural approach towards it, that okay, there would be many high level representations compressed into lesser spatial size. So for large number of spatial, like large number of features, like higher level features, you should have large number of kernels. But yeah, so number of parameters and number of compute complexity across different layers is tried to be kept constant. That's one thing. And also there is a natural analogy that why a large number of convolutional channels, like channel output, should be there for high level features. So this is how it works. Uh, so we have already seen a basic on like how training data is generated. Now to the testing part. Model was actually evaluated at multiple scales. So the final multi-scale model was evaluated at these three scales. So 224, 512, and an average of these. But not in a typical 10-way crop augmentation, which we have seen. So in AlexNet, we have seen this 10-way augmentation. What VGG does is like it converts their model architecture into a fully convolutional architecture. Like now coming from a network and network perspective, you can see that okay, this one by one, like what is this one by one and 4096? Basically, it is nothing but that okay, 4096 is my units, and since each unit is just a single value, I can say it is one by one. But what I can do is like I can convert this fully connected layer into a convolutional layer, like right, like suppose at the end I'm getting this 7 by 7 thing, and I want to convert 4096 values out of it. Okay, this is my hidden layer, and each unit. So what does each unit corresponds to? It corresponds to this 49 widths which are multiplied by this, right? And the same goes like here. So what I can say is I can also model this as a 7 by 7 and 4096 and whatever is here. Like here we have 5 and 12. So yeah, 5 and 12. So I can also model the same vector using this kind of convolution operations. Like 5 and 12 is my input channel, 4096 is my output channel, 7 by 7 is my kernel. So once I apply it onto this data, like this data, what I will obtain is like I'll get 1 by 1 by 4096. So this is how you can convert a dense layer into a convolutional layer. So using this thing, what VGG authors does is like they translated their network into a fully convolutional network, and like applied their VGG onto the larger images also, which were of size 384 and 512. They average their logits. So logits is nothing but the output value before applying the softmax. Okay, and then the softmax score was taken on top of that. So this VGG approach is kind of efficient in terms of like comparing with the multi-crop approach, which is 10 crop approach taken by the AlexNet. So but only thing is this multi-crop approach actually slightly outperform this dense evaluation approach of VGG. So this approach which we just discussed here is my dense evaluation approach. Okay, and this is 10-way crop augmentation approach. So what I can say is that okay, 10-way crop augmentation is better than this dense evaluation approach. But even the ensemble of both approaches, which is dense evaluation plus 10-way, this actually outperform either of these two. So from this, I can say that, okay, ensemble of these two approaches outperform these two. So I can also claim that, okay, so and since ensemble is outperforming either of these, so I can say that, okay, dense evaluation is complementary to the 10-way crop augmentation. Okay, and also dense method is significantly faster for a smaller image. Why that is the case? And let's look with an example. Okay, let's take an example onto this slide itself. Let's take here. So suppose this is my original image. Okay, and let's take a simpler size of 256. Okay, I'm just assuming. But what is the input size my VGE takes into account? So VGE takes 254 by 224 by 224. So you can take one patch here, 224. Like I'm assuming, like I'm just trying to draw a 10 crop, like five crops over here. So this is top left, this is top right, this is bottom left, and this is bottom right. And also I have a center over here. So certainly you can see that there are multiple like overlapping convolutions that needs to be performed if I am taking different like random crops out. Like for example, like let me just draw that thing separately over here. Let's I'm taking top left and I'm taking bottom right, just two for example. Then you can certainly see that convolution operation into this region needs to be performed like twice if I'm applying VGG separately on this crop and this crop. But this kind of issue doesn't come when I'm using a dense evaluation, where what I can do is like I can apply VGG onto the entire whole thing and produce an output. So now you can see like you can approximate entire VGG as a large convolutional kernel. So what I can say is like 256 minus 224 plus 1. So it come out to be 2. I guess I'm doing correct. Yeah. So what I'll be getting is like I'll be getting a 33 by 33 sized output, which I can average across the entire spatial dimensions using kind of a global average pooling. So I get a 1 by 1 output on which I can apply softmax. So this is the basic idea of this dense evaluation, that you won't be requiring multiple evaluations at different positions. So this dense evaluation kind of work efficient when these patches are kind of overlapping. Okay, it also has one benefit that in this dense evaluation, if I'm taking this crop, I'm not actually taking this crop out of the original image. So this way, these padding, these padded like pixels which are being used for padding, they are not zero. They are actually the data value. So, and certainly what it would be much better if you have padding from the data coming from the data itself instead of zero, all zeros. So yeah, due to these two reasons, this dense evaluation approach works faster than multi-crop augmentation for the smaller models. And also the results are kind of different from the multi-crop because the internal padding structure would be changed. Like certainly I will be have a padding of 0 here. So yeah, there would be a asymmetric padding, but yeah, at least on the one end, I'll have a data padding involved. So this is one approach which was obtained from like which was given from the VGE authors itself. So 10-way crop augmentation comes from the what I say AlexNet, but this dense evaluation comes uniquely from VGG. And certainly onto like since the 10-way also covers the horizontal flip. So for dense approach also you need to cover the horizontal flip. So kind of a mirror flip. And we actually average out the softmax for both of these flip, the original and the mirror flip version. So this is what different model architecture says. It is not my fault. It is from the paper itself that N is slightly not printed in a good quality. So yeah, the original baseline architecture was actually VGG 11. It was not VGG 16 or 19. And as we have discussed in past that okay, layers can be inserted. So what they have done is like author have first trained this configuration A, which is VGG 11. Then they have inserted this and this layer. These two layers were inserted, and the entire model was trained again from scratch. Okay, so this was not a kind of a fine-tuning procedure. The training begins from the scratch itself. Only thing is, their idea is that they need to train a deeper model without normalization. So yeah, that's what they have used the earlier model for weighting initialization. Once this configuration B was trained, then what they have done is like they have added these three layers, okay, to obtain a VGG 16. And once the VGG 16 is trained, they added more three layers to obtain a VGG 19 kind of thing. And then you have a max pool and a hidden layer, two hidden layers. I can say, like certainly I can say it is there. Then I have a fully connected layer followed by a softmax. So one thing to mention is there is another configuration, which is configuration C. It actually uses one by one convolution, and just as an attempt if it can better like capture the non-linearity. So certainly this configuration C performed better than the configuration B, but configuration D performed better than configuration C. So this is why into the final release versions, these one by one convolutions were not being used, and these two models were released into the public, VGG16 and VGG19, VGG16 and 19. So one reason I should be mentioning is that VGG was the first set of papers who released kind of two models at once. So why these two models? Because onto this multi-scale, multi-crop evaluation, these models kind of behaved similarly. Okay, so let's discuss from a role of contribution point of view. So the first contribution of VGG paper was to use smaller kernels, which says that okay, larger receptive field can be captured with lesser parameters if I'm using multiple small size kernel. This also allows me to build deeper model because there will be lesser parameters involved, so there is less chances of overfitting. Then having different small convolutions instead of one large convolution allows me to add multiple non-linearity after each small kernel. So this also kind of reduced the need for the network in network kind of approach one by one convolution. So this is one thing. So remove the authors, VG authors also removed the normalization layers. This not only saves the compute but also saves half of the GPU memory. And even till today, GPU memory is kind of a bottleneck for training large architectures. So yeah, like if authors would have used batch normalization after each of this, the model would require twice the GPU memory, and also it would take more compute. Okay, so then what is the analysis done by the authors? So there is literally zero to, yeah, it is almost no figure is present in the paper. But what authors have done is like they have taken these output vectors, which is like hidden layer representations of VGG architecture, and used them for downstream tasks, like for different tasks. And what they have done is like this led them to better generalization on multiple tasks. And so keeping in mind the VG16, VG19 architecture were released in public, and they are popularly being used in majority of the transfer learning tasks. So this is one of the reasons why I can say that okay, VGG can be used in for transfer learning, because the authors itself shows that okay, the representation that were learned on the ImageNet task, they are kind of generalizable and also achieves state of art performance in transfer learning for multiple tasks involving C410 and C100 and something related. So yeah, this is it. Like coming to the conclusion, I can say that um, for now we slightly touched upon like we started from what the ImageNet data set is, what is the neural network, what is the fully connected neural network, what is the CNN, what is the convolution operation specifically, how CNN are a subset of fully connected networks in terms of representation capacity. We started with the AlexNet literature, also discussed some of the training and testing data generation process and the optimization settings for that, the interpretation of the results which are being shown by the AlexNet papers. Then we moved into network and network architecture, where we have shown that okay, global average pooling is the key, and also large kernels don't capture non-linearity into the underlying data. So yeah, either one by one convolutions can be used, but also VGE paper actually removed the large kernels and replaced them by smaller kernels. So one by one convolution doesn't turn out to be of that help. But yeah, there is still a scope, as you can see in these architectures, that inserting one by one convolutions also help slightly gain the performance, but three by three is a better idea. One thing to mention here is that since I've already mentioned that VGG 16 performed kind of equivalent in VGG 19, why was that the case? Like we can think upon it. That certainly, like VGG 19 is not an independent architecture of VGG 16, and VGG 16 is not an independent architecture of VGG 13. So the model building flows like that. Like you have a VGG 11. After you have trained VGG 11, you are training a VGG 13. Then you are training a VGG 16. On top of that, I'm training a VGG 19. So what I can certainly say is that as like since you are not initializing these weights randomly, so if the entire classification kind of performance was captured by this VGG 16, the additional three layers which were added at these positions, they have little to nothing to learn with respect to the final classification performance, because these layers which are coming from the VGG 16, they have already like quite well in terms of the discrimination capacity. So yeah, like this way, like if someone is trying to insert random layers in between in the VGG fashion, like I can say that okay, performance can saturate at point of time. So I can say that okay, here we have VGE 16 and here we have VGE 19, and performance is kind of similar for these two models. Like it will asymptote at a point of time. So yeah, this is a basic brief around these different model architectures. And this is from where, like, yeah, we also discussed some different computer vision applications. And like you can look into these slides and come up with any doubt and mention them, or like communicate with me separately, like over different channels you can find me to reach out. So yeah, this is how it is. And like moving forward, we will be presenting the ResNet architectures from the next session. Like ResNet is a popular architecture, and so I can mention here itself that ResNet has multiple variants, and I like every one of you to go through this video to understand what VGG architecture is, AlexNet, network and VGG. So from ResNet point of view, we will be covering different architecture, not only ResNet, we will be covering ResNet v2, then we will be covering ResNext, then we will be covering RegNet, then we have SERES next. Then along these model architectures, we also have something of this sort, like we have stochastic depth behavior of ResNet. So this is one of the key paper which analyze that, okay, what is how, or also we have one, like basically this allows us to train network faster and also better. So this is one of the paper. Then we have another paper on ensembling behavior of ResNet. And also into the model architectures, we also have one paper which is wired ResNet. So we will be looking into multiple ResNet architectures. And there is one latest paper in 2021 or 2022, I get, which is ResNet RS. Okay. So like it is kind of revisiting ResNet, and different techniques were actually combined in this paper. So yeah, there is a large body of work around the ResNet architectures. And post this discussion onto the VG, we will be moving into this. This is all for now. Like, let's see you into the next discussion and connect over there.